The power of sight, honed by evolution over millions of years. It's how 95% of animals perceive the world. It can determine who gets to eat and who gets eaten. Sophisticated eyes give animals the power to see in 3D, in panoramic widescreen, and even in ultra-high definition. Some can see colors we can only dream of. Others view a world that is completely invisible to us. In nature's book, the eyes have it. Welcome to the world of supersight. On the African savannah, a classic showdown is about to unfold. An ancient contest between two masters of speed and agility. The cheetah is the world's fastest land animal. In short bursts, it can top 60 miles an hour. The impala is slower, but has greater endurance and the ability to leap and dodge. But as the chase gets underway, another battle is also raging. This is a contest of vision, because when it comes to predator and prey, what you see is what you get. This mother cheetah has 3-year-old cubs. They're growing fast and need to eat every day. But it's been 2 days since their mother made a kill. As she prepares for this morning's hunt, she draws on the first weapon in her arsenal: her spectacular vision. The anatomy of her eyes has evolved for just this purpose. Human eyesight is sharpest in the middle of our circular field of vision. By contrast, the cheetah has a concentrated horizontal strip of nerve cells across its retina, which allows the cheetah to detect even the tiniest movement on the horizon, as much as 3 miles away. So it sees most accurately across a narrow horizontal band, which is ideal for spotting prey across the wide, flat savanna. She scans the impala herd for a vulnerable animal and finds one, a young male that's lagging behind the group. Now that she's within striking distance, a new set of visual tools comes into play. The cheetah's distinctive tear marks, running from eye to mouth, help reduce the sun's glare, like the black markings American football players put under their eyes. And her flat face and large forward-facing eyes give her another edge: binocular vision. Binocular vision is when the brain combines the separate images seen by each eye into a single image, like a pair of binoculars. Because each eye captures a slightly different view, the brain can build a single 3-dimensional image with a sense of depth. It makes the cheetah brilliant at judging the precise distance of its prey, a critical skill in a hunter. The heightened depth perception also helps it break the camouflage of an animal trying to blend in against its background. As the predator closes in, it looks like curtains for her quarry. Not so fast. The impala wouldn't have lasted as long as it has if it didn't have a few tricks of its own. Because while the cheetah's eyes have evolved to hunt, the impalas have evolved to detect danger. Predators' eyes look ahead at what they're trying to kill. But prey animals must be aware of their entire surroundings. Most have sideways-facing eyes, which offer a very wide field of vision. Impala's eyes point in almost opposite directions. They don't miss much. And their eyes have slotted rectangular pupils that reduce glare from above and below, while maximizing light from the front and sides, because that's where the danger usually comes from. These adaptations give the impala an astonishing 300-degree arc of vision, a third wider than that of the cheetah. Even when they bend down to drink, the impala's pupils rotate to stay parallel to the ground, making it tough for predators to sneak up behind them. Just a slight turn of the head can give them a full 360-degree field of view. With defense vision like this, a lone impala has a good chance of spotting a stalking cheetah. And a herd has many pairs of eyes on the lookout. One spots the danger and barks out an alarm. The cheetah's cover is blown. Now it must rely on the skill it's most famous for. It accelerates from 0 to 60 miles per hour in just 3 seconds. Faster than a Ferrari. But even now, vision holds the key. Its inner ear anatomy means the cheetah can maintain visual stability, keeping its eyes focused and its gaze locked on its prey, even at this breathtaking speed. The impala has a head start, and its eyes scan for the best escape route. The cheetah can only sustain 20 seconds at its top speed. But it's enough to bridge the gap. The impala's panoramic vision gives it a fighting chance. But as the distance closes, the balance tips back to the hunter. This time, the 3D precision of the cheetah won out. An evolutionary arms race has made cheetahs and impalas nearly evenly matched, but very different in their visual tools. But not all animals have the luxury of being quite so specialized. Some are both predator and prey. With them, evolution has had to make a trade-off. Enter the meerkat. These small carnivores live in groups of about 20. They forage for lizards, insects, and rats out on the open scrubland. Their short-range vision is weak, so they use smell to sniff out their prey. If they had to depend on their eyesight to find food, they'd go hungry a lot. They traded close-up vision for excellent long-distance sight for a very good reason. While they're foraging, they're extremely vulnerable, especially to predators from above. So there's always a sharp-eyed sentry scoping for hungry birds of prey. Like cheetahs, meerkats have binocular vision, so they can judge distance well. They also have the dark fur around their eyes, which cuts the glare from the sun and helps them detect a raptor from more than half a mile away. the sentry spots an eagle in plenty of time to sound the alarm, which sends the rest of the troop running for cover. Underground, a translucent second eyelid, called a nictitating membrane, acts like a windshield wiper, removing sand from their eyes with every blink. Like impalas, meerkats have evolved horizontal pupils to maximize their field of view and anticipate threats without turning their heads, whether the threat comes from above or below. A Cape cobra. Many a meerkat has met its end by the bite of this venomous snake. But there's no use trying to escape a snake by diving into a burrow. So the meerkats stay above ground and mount a gang defense. They're members of the mongoose family, famous for standing up to snakes. With 20 pairs of eyes on the enemy, they leave this stealthy hunter nowhere to hide. Cheetahs, impalas, and meerkats have evolved 3 different types of vision, each suited to their lifestyle and habitat. But eyesight like theirs didn't develop overnight. It took millions of years to evolve. There was a time when no creature on the planet had eyes, a time without vision. The first organisms that could detect light were photosynthetic bacteria that lived in the ocean. They gained an advantage because light helped them manufacture their food. Then, about 500 million years ago, animals began to do more than just sense the presence of light. They began to determine form and shape. A vestige of this primordial past can be found at the bottom of a gloomy lake. The flatworm is a living fossil, the direct descendant of a creature that lived 550 million years ago and has changed little since. It doesn't have a circulatory system. It doesn't have a respiratory system. But it does have a nervous system, with the first hint of 2 eyes. The 2 black spots on the top of its head resemble the very first eyes on Earth. Each cup-shaped eye spot is filled with light-sensitive cells called photoreceptors. They can do more than tell light from dark. When light hits the eye spot, the lip of the cup casts a shadow, so the flatworm can also tell what direction it's coming from. The result is a world in shades of grey, just enough for the flatworm to sense and avoid danger. To be able to see even dimly in a world of blind creatures would have been an enormous advantage. And evolution selected for that advantage, though the forms it took were often surprising. Not much light reaches the bottom of the Mediterranean Sea, where this spiny sea urchin lives. Yet somehow, in the twilight, the sea urchin knows exactly where it's going. It can navigate across the sea floor, find food, and hide from predators, just as if it had perfect eyesight. But if the urchin can see, where are its eyes? For years, zoologists were mystified, until they made a remarkable discovery. There are dozens of light-sensitive cells on each of the urchin's many tube feet. When researchers looked further, they found more photoreceptor cells. not just on its feet, but all over the urchin. Its entire body works like a giant compound eye, with photoreceptors that not only detect light, but also form vague images. Its light-sensitive cells can catch the shadow of a cruising predator. And while it can't outrun its foe, it can lift up its spines in a defensive posture. Despite its alien looks, the sea urchin is more like us than we might imagine. Scientists believe the genes responsible for photoreceptors in sea urchins are the same genes that led to the development of eyes in all animals, including humans. Photoreceptors like those found on sea urchins were the first step in the development of true vision. But mollusks took a major leap forward in the story of sight. They evolved a retina, an organized light-sensitive layer of tissue in the back of the eye. This technological leap might be surprising for an animal that doesn't need to see in order to eat. Such as this elegant file clam, which simply filters particles of plankton that drift by in the current. But it does need vision to stay alive. That's where a retina really comes in handy. The file clam not only has a retina, it has two per eye. One for perceiving brightness like an approaching predator, the other to detect shadow for threats from above. Multiply that by the 20 eyes it has dotted around its shell, and you have an extremely effective early warning system. The file clam slams shut and shoots away from danger by jet propulsion. Its 20 eyes and double retinas have left its attacker in the dust. Another mollusk, the scallop, sports up to 200 eyes on tentacles at the edge of its shell. Like the clam, each of the scallop's eyes have two retinas, but the scallop got an upgrade. A scallop eye works like a reflecting telescope, using microscopic mirrors to gather as much light as possible. The mirrored layer in its eye is made of a crystalline substance called guanine. Light entering first hits the reflective layer at the back of the eye and bounces some of the light onto two retinas. One retina focuses on peripheral vision, which helps the scallop assess its surroundings. The other retina focuses on what's right in front of the scallop. So the scallop can spot danger earlier than a clam can, giving it plenty of time to escape. Once the retina evolved, it was here to stay. And some mollusks now possess quite sophisticated vision. Strange as it may seem, this creature is also a mollusk, like the clam and scallop. Cuttlefish have been swimming the oceans for 21 million years. As a cuttlefish cruises the reef, it uses its keen eyesight to assess its surroundings and blend in. It's known as the chameleon of the sea. Thanks to elastic pigment sacs in its skin, called chromatophores, it can change its color and pattern, so it can camouflage itself from predators and sometimes scare them off. But its shifting colors and patterns have another important purpose: communication with other cuttlefish. This large male on the left has spotted a potential mate, so he changes color to give her a real eyeful. But here's the twist in this relationship. Cuttlefish are actually colorblind. We can see the changes in his skin color, but she can't. So what's the point? Scientists have discovered it's not the color that's important. It's the physical quality of the light and how it's polarized. When light waves are emitted from the sun, they travel in all directions at every angle. They're unpolarized. But when light hits certain objects, only the waves traveling at one angle can reflect off it. That's polarized light. Humans can't perceive polarization without special sunglasses, but a cuttlefish can. They can detect the tiniest variations in the angle of light reflecting off an object, including each other. So while we see the male changing color, a female sees an intensely detailed mosaic of patterns. Relying on polarized vision, the male can stand out proudly to other cuttlefish while being nearly invisible to everything else. Not a bad survival trick. Mollusks have made a lot of advances in the evolution of eyesight. But only one ever made the great leap from sea to land. The snail. Snails first evolved in the ocean about 500 million years ago. Some stayed in the water. Others slowly crawled out onto land about 350 million years ago. When they did, evolution made a few changes. Like many of their seafaring cousins, their two eyes moved from the base of their tentacles to the tips. It gives snails a kind of periscope for looking around in all directions. That said, snails don't see particularly well. They don't really have to, as they're mostly nocturnal. But they do have a crucial adaptation retained from their sea-dwelling ancestors: a lens. The lens is a transparent structure that focuses light to form a sharp image. It improves a land snail's ability to sense approaching danger. And while it's not going to outrun a predator, at least it can retract into its shell, where it has a better chance of surviving. Changes in environment often drive visual adaptations like this, whether the move is from the ocean to land or the other way round. The ancestors of fur seals evolved on land. They're actually distant cousins of bears. But about 25 million years ago, their ancestors returned to the sea. Their limbs became flippers. Their spines grew more flexible. And they developed the ability to hold their breath for over an hour. But readapting to the sea posed a vision problem. The seal has to function in two worlds, so it needed eyes that could handle both environments. Out of the water, a seal's eyes narrow to a slit, and its pupils constrict to a pinhole, so that bright light won't damage its supersensitive eyes. But when it takes the plunge, its eyes transform. Fur seals' eyes can adjust to the shift from light to underwater gloom 5 times faster than a human's. Their pupils become huge. This dramatic adjustment allows them to spot speedy fish and camouflaged crustaceans, even in the perpetual twilight of the depths. Like most mammals, the fur seal's retina contains two kinds of receptor cells. Cone cells, which are responsible for color perception in bright light, and rod cells, which only register shades of gray in low light conditions. Seals have a large number of these rod cells, which help them see in murky water. But as is often the case, advantage in one area means a loss somewhere else. They have relatively few cone cells, so they can only see a very limited range of color. But the underwater world in which they hunt appears mostly gray anyway. So it makes sense to devote more resources to rods than cones. As different as fur seals, cuttlefish, and cheetahs are, their eyes are actually quite similar. They all have versions of what's called a camera eye, where each eye uses a single lens to direct light onto the retina and create a single image. But this isn't the only way complex sight has evolved. While mollusks and mammals developed their camera eyes, insects took vision in a totally different direction, with compound eyes. Each compound eye can be made up of thousands of units, each with its own lens, each creating its own image. It's like having a lot of little eyes, all looking in different directions. The dragonfly first appeared 325 million years ago. It's an aerial acrobat and a formidable predator, able to chase down and grab other flying insects in mid-air. It gets that laser focus from up to 30,000 optical units, called ommatidia, in each compound eye. Each one picks up a tiny fragment of visual information. These overlapping images are assembled into a kind of mosaic, creating a detailed picture. They're the biggest compound eyes of any insect, enabling the dragonfly to see in any direction except directly behind it. And that's only the first of its visual superpowers. Humans and other primates have three types of color-detecting proteins, or opsins, allowing us to see color in combinations of blue, green, and red. The dragonfly eye has up to 10 times as many types of opsins as we do. It means they see their world in a riot of colors invisible to human eyes, including ultraviolet light. Scientists think this helps them pick out fast-moving prey against contrasting backgrounds. And there's more. Our vision feels seamless, but it actually works like a movie camera. Human eyes capture up to 60 individual images a second, which our brain blends into moving footage. But at only 60 frames a second, fast action can still seem a blur. Dragonflies capture as many as 300 images per second. So when we see the blur of a fly in the air, a dragonfly sees a crisp image of its prey, frame by frame. Much easier to pursue and catch. A dragonfly may only be a couple of inches long, but its sophisticated vision makes it a more effective predator than a lion or a great white shark. It makes sense for a flying insect to have compound eyes. But this arachnid needs a different bag of tricks. This jumping spider moves stealthily through the foliage on the hunt for something to eat. Instead of one pair of compound eyes, it has 4 pairs of simple eyes, each pair doing a different job. There's 1 pair of huge principal eyes and 3 sets of lateral eyes. fly wanders too close, triggering the lateral eyes which detect motion. Now it deploys the principal eyes, which function like telescopes, enabling it to lock onto its target. The jumping spider can leap 6 times its own body length. That's like a human jumping the length of a school bus. But more important than distance is precision. It can gauge striking distance down to the tiniest fraction of an inch. When its behavior was first observed, the spider's amazing depth perception was a mystery, because its eyes are too closely set for binocular vision. But the spider doesn't see depth the way we do. Instead of combining 2 images to create a 3D image, it processes the same image through 4 consecutive layers of photoreceptor cells. When it spots its prey, the image hits layer after layer, getting blurrier each time. It's called defocusing, a form of depth perception unique in the animal kingdom. The spider's brain then calculates how far it needs to jump to land precisely on its target and deliver a lethal bite. The jumping spider's vision is impressive, but this arachnid boasts the best night vision on the planet. Better than cats, better than owls. The ogre-faced spider. With bulging eyes and protruding fangs, it has a face to match its name. Like the jumping spider, the ogre-faced spider's eyes face forward like giant spotlights. They're the biggest eyes in the spider world. When night falls, the spider starts working on its web. But that's not all it's building. At night, it grows a light-sensitive membrane inside its eyes. They're like night vision goggles. Because they're so sensitive, the membrane breaks down and must regenerate every night. When it's finished spinning, the spider carefully deposits some spots of white feces at strategic points on the forest floor. They act like the sights on a gun, helping it aim. Hanging head down, from the trapeze of silk, the spider holds the net in its front legs and waits. The enormous curved lenses gather in all available light, helping it to spot a cricket in virtual darkness. The cricket appears 12 times brighter to an ogre-faced spider than it would to a human. When the spider has the target in its sights, it casts its net with devastating accuracy. It enfolds its victim with sticky silk. Dinner is served, thanks to its extraordinary eyes. Throughout the animal kingdom, one of the greatest assets is the ability to see in color. Even the earliest vertebrates could do this, more than 500 million years ago. But when mammals first appeared, about 200 million years ago, they took a step backwards. They inhabited a world dominated by dinosaurs, so they tended to be active at night when the reptilian predators were off duty. Seeing color isn't much use in the dark, so early mammals lost much of their color vision. they became what's called dichromatic. That means they had just two types of cones that detect only two colors, green and blue. Most mammals are still dichromatic. With eyes able to detect green and blue, they can identify about 10,000 different hues. But by about 23 million years ago, the dinosaurs were long gone, and one group of mammals became diurnal, active during the day. Primates. Now that they were up with the sunrise, they started to regain the color vision they'd lost and adapted it even further. Over time, they evolved a third kind of cone in their retinas, which transformed the world around them. Now they could see many shades of red, orange, and yellow. Today, most primates retain this ability, including these vervet monkeys. Vervets spend much of the day foraging for insects, shoots, leaves, and ripe fruit. Their ability to pick out red, orange, and yellow from a green or brown backdrop means they can spot ripe fruits and berries more easily. Three-color, or trichromatic vision, helped early primates to improve their nutrition and left us an evolutionary gift. Humans can see the world in more than 10 million shades of color, all thanks to our fruit-eating ancestors. While primates have reclaimed the ability to see in many colors, birds are far better at this than we are. Case in point, the pigeon, a common sight in our cities and towns. But there's nothing common about the way it sees. As colorful as it is, our world is drab compared to the dazzling technicolor world a pigeon sees. Here's why. Like primates, birds can detect red, blue, and green. Plus, they can sense ultraviolet light. This is called tetrachromatic vision. Mammals' cone receptors are simple, but pigeons have double cones, a regular cone cell with a second cone wrapped around it. This tetrachromatic vision enables pigeons to see about 100 million distinct colors, 10 times the number we humans can see. They use this keen color vision to locate food. Some fruit have waxy skins that reflect UV light. For the pigeon, these fruits are like lights on a Christmas tree. The pigeon's eyes have another surprising trick to help perceive the colorful world around them. Some of their cone photoreceptors carry oil droplets. The oil bends the light before it hits the receptor to further heighten color perception. By bending the light like a prism, it increases the numbers of colors that can be differentiated and turns up the contrast between them. This first-rate color discrimination would be astonishing all by itself. But there's more. The pigeon can pick out a morsel of food while cruising at speeds of 50 miles an hour, when all most animals would see is a blur. An unusually large portion of a pigeon's brain is devoted to visual processing. It can process images 3 times faster than a human. A movie in a theater would look like a slideshow to a pigeon, much as it would appear to a dragonfly. Evolution favors anything that gives an animal a survival edge. While a pigeon's 4-color vision is impressive, Raptors have even more demanding visual needs, so they push the envelope even further. The peregrine falcon is the fastest creature on Earth. Since it's a predator, what it eats is usually moving too. Somehow, the falcon must lock onto its target, track its trajectory, and strike a killing blow, all while diving at speeds faster than a bullet train. It pulls off this feat with some of the best long-distance vision of any animal. The sheer size of the peregrine's eyes in relation to its head is a dead giveaway to how important they are. If humans had the same proportions, we would have eyes as big as oranges. Like us, the peregrine has binocular vision, which helps it to calculate distance accurately. But its real superpower is the ability to spot small prey from over a mile away. Thanks to a feature that's unique to raptors. At the back of its retina are two small depressions packed with cones called foveas. One fovea focuses on fine details, like a macro lens. The other gives the birds incredible telescopic vision, allowing their eyes to home in on prey like a zoom lens. They can pinpoint a mouse or a pigeon from over a mile away. And this unlucky pigeon has been spotted. The peregrine makes its move. It can dive more than 180 miles per hour faster than a pigeon. Even in its high-speed plunge, its telescopic fovea keeps it dead on target, like a guided missile. The falcon's blazing attack only works because it has the vision to match its speed. It's that deadly combination that makes it such a formidable predator. But not even this extraordinary creature can lay claim to having the best eyes in the animal kingdom. The holder of that title might come as a surprise, but perhaps it shouldn't. After all, sea creatures had already been developing vision for 400 million years before the first birds opened their eyes. That's a lot of time to experiment and perfect design and function. So it makes sense that the most advanced vision belongs to a resident of the ocean floor. Meet the peacock mantis shrimp, which technically isn't really a shrimp at all. This colorful beast is small enough to fit in the palm of your hand, but it's a visual powerhouse. It has hexnocular vision. That's 6 pupils, 3 in each eye. Each piece of its visual apparatus is dedicated to a specific task. The upper and lower sections are specialized for form and motion. The midsection has 6 rows of ommatidia that perceive color and can sense both UV and polarized light. The mantis shrimp's eyes are mounted on stalks and move independently. They scope out its surroundings, giving it a comprehensive 360-degree field of vision. With each eye processing 3 different images, the mantis shrimp can generate 3-dimensional depth perception independently in each of its eyes. The only animal in the world that can do this. Thanks to eons of evolutionary fine-tuning, this tiny crustacean boasts the polarized vision of a cuttlefish, the 3D vision of the cheetah, the UV sensors of a bird, the movable eye stalks of a snail, and the near 360-degree vision of the dragonfly, all in one small package. This odd-looking little thing's got it all. And it processes incoming images in the eyes themselves, rather than sending them onto the brain for processing. Bypassing the brain speeds up reaction time, and lightning reflexes are just what you need when you're one of the world's most aggressive hunters. The mantis shrimp is the fastest draw in the ocean. It unleashes a spring-loaded club that it fires with the acceleration of a bullet from a gun. The force rips the crab's claw clean off. It isn't much consolation to the unlucky crustacean that its killer possesses the most complex eyes in the animal kingdom. But it raises the question, did the mantis shrimp really need all that visual power just to punch out a crab? Scientists are still looking for the answer to that one. From the very first light-sensitive cells, nature has had 540 million years to experiment with vision. An experiment that continues to this day with eyes of every conceivable form and function. After all, there's no right way to see the world. It's all about giving animals that extra edge to meet the challenges of their environment and to triumph in the battle to survive.
Hey Love Nature fans, be sure to like and subscribe to catch all our wild animal stories. Get closer to nature right here on YouTube.